Welcome to this YouTube channel. Today I'll be introducing you to molecular modeling. And to be more specific, you'll be learning how you can optimize the structures of molecules using Chem3D, Avogadro, and Spartan. Now, molecular modeling involves using computational methods to represent and study the structure and behavior of molecules, and you would find that it's used in different fields like chemistry, biochemistry, in the discovery of drugs, in predicting how materials will behave and how they interact with other materials. We also use it in medicine. And the basic thing we use molecular modeling to do is to predict how molecules will interact at an atomic level. Now, by understanding how they interact at the atomic level, we are able to predict their energy profile, and through that, we can also consider how they will react and their stability. So it gives us information on their reactivity and their stability, and by extension, you can use it to know how they will behave in a particular system, especially in drug discovery. You can also use it to know how they will interact if you're considering material science. Now, I say this because it's important to know that molecular modeling is becoming key for every part of science. Now, one basic thing we do in molecular modeling is geometry optimization. So it's not just enough to draw the structure of a molecule. It's important that your molecule, the structure you've drawn, is representative of that molecule at a stable state. We often will believe that in nature that molecules will exist at a lower energy with a lower energy structure. So what we do in optimization is to locate the geometry with the lowest energy structure, and that's what we use for other calculations in computational chemistry. Now, how do we do that? We simply try out different geometries and then obtain their energy till we get the one with the lowest energy. And we do this using computer algorithms. Basically, optimization now from a mathematical point of view refers to looking for the stationary point of a function where the derivative is zero. And that's what is being done by those algorithms. Now, today I'll be showing you how you can carry out this geometry optimization using three softwares, using Chem3D, using Avogadro, and using Spartan. Let's go to practical session. So the first thing you're expected to do is to um, first of all, let's start with Chem3D. So I would open Chem3D. You must have installed ChemDraw, the whole package. Once you install the whole package, it will come with ChemDraw. It will also come with Chem3D. Now, so this is Chem3D. Now I will also open ChemDraw because I would like to start by drawing a structure. Okay. Now, so let's draw a structure. This, this, okay, this, and let's say this is O, let's call this OH, and then let's say this is NH2. So first of all, we've drawn our structure in ChemDraw. Now, if you've not learned how to use ChemDraw, I have a video on it, so you can always check it out. So let's clean up our structure, and then I'll try to, let's find out the name of this compound. So 1 amino pentan 2 ol. So copy the structure and then let's put it here, paste it here. Now, so this is the 3D structure of the compound, and you can see now this is a particular structure that possesses a geometry, but the question is this geometry the one with the lowest energy? And that's what we use optimization for. We need the optimized structure for other computational works. Now you can carry out optimization using different models of force fields. You can use the molecular mechanics force field. You can also use the Merck molecular force field. And so I will show you how to use the molecular mechanics force field. It's the simplest. So what you just do is just click here. Now you can see, so interesting. So it gives us the total energy. You can see that. So total energy of this geometry, which is assumed to be the lowest, the one with the lowest energy, is 5.90 kilocal per mole. That is using this model. So what I will do is I will simply copy it somewhere. Okay, let me copy it. So I should just copy from here. Good. So copy, then I'll store it in a notepad. Control N. So total energy for what's the name of that compound? 1-amino pentyl. So let's just leave it like this. It's this. Now, so now there is also another force field we can use, and um, if you want something fast and a bit reliable, you can just use the molecular mechanics. However, if you want something more detailed, you can use the Merck molecular force field. You can see it's MMF94. So what we do is click on calculations, go here, and then select perform MMF94 minimization. So I'll do that. So and then good. Now you can see that the energy of this system is calculated as 23.2193 calories per mole. So in this case, what did I do? I used a different force field. Let's see, the values are, now you can see that the values are not the same. So this was when we use, this was for molecular mechanics, and this is for MMF94. Now, in this case, I drew the structure in ChemDraw, and then I transferred it to Chem3D, and then I simply optimized it to obtain these structures. Now, what often happens is that a lot of times we don't draw these structures, we import them from databases such as PubChem or ChemSpider. So when you've imported when you've downloaded a structure, always know that that structure has to be optimized. Just using the structure for computational work will give you a wrong answer. So it's important to optimize that structure. Sometimes we call it minimize. You can optimize the structure, and then what it gives is what you would use. So let me show you how to do that. So let's say I downloaded um, a structure from PubChem. I've done that, so I will just look at it. It's in this folder, molecular modeling, and then I downloaded it as an SDF file. It was a 3D structure. So what I can do is I can open it. Now you can see that structure. So this is the structure, and what I intend to do is to obtain the optimized structure for this compound. So what do? I don't want to just go through molecular mechanics. I want to use the Merck molecular force field. So what I will do is go to calculation and go here, MMF94, and then if you intend to set this up, that's a different thing now, but I don't want to do that. So go to perform MMF9 for minimization. So now dielectric constant 1, okay. So this is fine. We don't change anything here. And then if you want to change the number of reiterations, this 500, you can choose to change it. So, and then I'll just run. Now, it has given us the answer, and the answer is minus 33.7007 kilocalories per mole. So I will save that. The structure is, you can check it on PubChem. The ID is 77999. So I will save it as MM94. So the final energy is negative, that is minus 33.7007. Now, and let's put the ID, so CID 77999. Okay, interesting. So now, so you have learned how to obtain the optimized structure or carry out geometry optimization using Chem3D. Now, how do you do that using Avogadro? So let's use Avogadro. Now, so what you simply do is to have your Avogadro installed. It's very easy to install Avogadro, and then we are going to carry out geometry optimization. So go to File, go to Open. Now let's navigate to, okay, so it's here, molecular modeling. Now this is that compound, the structure of the compound we downloaded from PubChem. So let's open it. Oh, you can see how it looks. Now, so what we can do is to optimize the structure. Simply click on this, and then we want to use the MMF9 for force field. And then we are now carrying out molecular dynamics, so we can fix atoms are movable, ignore atoms are movable, and then if you intend to work with that, but I won't check anything, so I'll just click on this. Now you can see that it's obtaining different energy values. Now the optimized structure will be when this derivative is 0, when delta E is 0. So it will go on for quite a while. Now while we are still doing this, this is how we carry out geometry optimization using Avogadro. Let me lead you to Spartan. So you should have installed Spartan. Spartan is a powerful software that is used for molecular modeling and computational chemistry. It's very powerful, and then it's robust. Now you can use it for DFT work and many other things. So what we can do is, I will also open that structure. So go to open, or you can choose to draw the structure, but I'll just be opening it. Then click on all file. Now this is the compound. Good, you can see the structure now. So once you've imported it, the next thing to do is go to setup, click on calculations. Now here you choose the equilibrium conformer. Like I told you, geometry optimization obtains the conformer with the lowest energy, and that's often called the what? Equilibrium conformer. So that's what we'll be using. Now to carry out geometry optimization, we'll be using molecular mechanics, but the force field we'll be using will be the Merck molecular force field. Now, and I'll click on this. Now I often want to type keep verbose, so it keeps everything. So what we can do is, once you've done, remember what you do, check and make sure it's equilibrium conformer molecular mechanics, and then you don't compute anything since you're just carrying out geometry optimization. So simply submit. Now if I want some, it will just, let me save it as this compound this. So it has started. Now to check what is happening, click on options and go to local monitor. Now and you will see, you can see that. So it's computing the energies of different structures. You can see that until we obtain the one with the lowest energy. So now let's still go back to see. Now you can see that delta E is not zero yet, so it's still calculating the energies. Now, I have the sound, so you can see that Spartan is quite fast. So now this is the structure. You can see this is the structure that has the lowest energy. We can call it the equilibrium conformer. Now to find out more information on this structure, click on the output. Now if you click on the output, you'll see what it did and you'll see the value it gave us. So let's see. Oh, good, interesting. So the lowest energy conformation was this, minus 158.6687 kilojoule per mole. So I'll copy it and then I like to paste it here. Now this was when we used, don't forget this was when we used Chem3D. Now, so when we use this is when we use Spartan, so I will just change this. Ctrl C. So this, so this is when we use Spartan. Remember when we say final energy, we are talking about the energy of the conformer with the lowest energy. So you see it tells us that the lowest energy conformation was minus 158.6687. Remember this is in kilocalories per mole, while this is in kilojoules per mole. Now let's go back here and then let's see. Now it's still trying to get that. Now while we do that, let's see, let's carry out energy conversion and see if the values gotten from Chem3D and that from Spartan seem to be quite close. So let me use a calculator. And then, so I'll be using energy. So this is in calories. So our value, let's go back there. Our value for Chem3D was minus 33.7007. So, okay. So 33. Now, but remember that it's in kilocalories. So that will be 700. Good. 007. Okay. Okay, good, yes. Now 0.7, we have this 0.7. So in kilojoules, that's actually about 141 kilojoules, while what we obtained from Spartan is minus 158.687. There are times you would have so this equivalent to 1 minus 141.0037. Now there are times you would find out that the different algorithms give you answers that are a bit different, but that does not mean it's not correct, because there are different algorithms. They will use different paths to get the compound, I mean the structure with the lowest energy. So let's still see this. Now it's taking a while for Avogadro. Now it has completed, and you can see that the value it gives us is that the energy for the equilibrium conformer is minus 145.047. So we obtained it. So for so let's say so let's paste it, but in this case this was Avogadro, and but our answer was minus 145.047 kilojoule per mole. So when delta E is 0, that means this structure is the optimized structure. So when you've gotten the optimized structure, what you do is that you save it. You can save. So it's important you save it as being optimized. If you don't save it, you can lose what you've done. So, but if it's on Spartan, it would have saved it that way. The same thing for Chem3D. You can now choose to save. Let's save it as optimized. So we save it as optimized, and then depending on how you want to save it, I'm saving it as a multiple file, so you can save it, so that's fine. And then you can see that. So you can also choose to save this and then save it using the name you intend to save it with. So I'm going to save as maybe optimized, and then can save. Then the same thing, you can also just for Avogadro, you can also choose to save with the name you want. Now, so this is how you carry out geometry optimization. Now, you don't need to use the three, you can just use one, but I've shown you that you can use any of these softwares to carry out geometry optimization. So I would love to hear from you. Please don't forget to like our page and make sure you subscribe. We'll be providing more information when it comes to computational chemistry related work. Thank you for listening. Bye bye.